All right, this is the second part of video 6.2.4. I thought both of these examples would have been in short enough time for one video, but I don't want the video to run too terribly long. So if you haven't watched the previous video, you need to go watch it before continuing this one. All right, we're going to solve tangent squared theta is equal to 3. Now this is a basic quadratic trig equation. It's only got one trig function and it's squared. But unlike the previous one, which I'll show you, unlike the previous one, it doesn't have two trig functions. It's only got the one, or two terms, I should say, with tangent. It's only got one term. Another technique for solving quadratic equations is if there's only one term with the variable, or in this case, the trig function, you don't need to factor or use the quadratic formula. Just start isolating the trig function like a basic linear. So unlike the previous example, I just said all this. This only has the quadratic term, so we can easily isolate the trig function using square roots. Don't forget the plus minus. We took the square root of both sides of this equation. Algebraically, that means we need to bring in a plus minus on one side. We'll bring it in on the right side. And of course, the square cancels the square root on the left. So we get tangent of theta equals plus or minus square root of 3. Now we have two separate linear equations. Tangent of theta equals square root of 3, and tangent of theta equals negative square root of 3. Now, within the first period, which is 0 to pi, it's tangent. Tangent theta is positive in quadrant 1, so we'll have a solution there, and negative in quadrant 2, so we'll have a solution there. Now, the reference angle for each is tangent inverse of square root of 3, which is pi over 3. Because when you do the reference angle, you take the inverse trig function of the absolute value. And when we take the absolute value of this expression, it comes out to be the square root of 3. So we'll have the same reference angle in each quadrant, pi over 3. And in quadrant 1, that's the solution, pi over 3. But in quadrant 2, it's pi minus pi over 3, which is 2 pi over 3. Okay, so maybe I could have done this one on the end of the previous video. It didn't take that long. The general solutions are the previous solutions plus pi n, because the period is pi, where n is an element of the integers. All right, so that one went a lot faster than I thought. So before I go back to the now you try, let's just quickly review what we just saw in all the quadratic videos, since this video is only 2 minutes into it right now. So in the quadratic ones, the idea was to make a substitution, which like on this one, which turned it to a quadratic equation. We solved the quadratic equation, undid the substitution, and then solved each of those subsequently, and then turned them into general solutions. But when we had this one and did the substitution, and we had to use quadratic formula, which gave us ugly answers. Beware of ugly answers because they may not be obvious whether or not they're in the ranges of the trig functions, which means you have to think about their decimal approximations. 1 plus square root of 5 over 2 is bigger than 1. It's outside of the range of cosine, so that equation had no solution. 1 minus square root of 5 over 2 was in the range, but it was negative, and so we had to follow accordingly. And then when we did this one, we didn't have to factor or use the quadratic formula because we just had the single squared trig function. Isolate it, which in this case only took the one move of square rooting both sides, and then attack both of them similarly. Just remember, everybody's period is 2 pi except tangent, and it's reciprocal cotangent. So whenever you're talking about periods, whether it's the interval that you're finding the general solutions, the specific solutions, or the period multiplier that you tack on to the specific solutions to get the general solutions. It's 2 pi unless we're talking tangent or cotangent, in which case it's pi. All right, now you try. Pause the video and try the following. Number 1, solve 2 secant squared theta minus 5 secant theta plus 2 equals 0. Give general solutions. I'll give you a hint. It will factor. You're welcome to use quadratic formula. And number 2, solve 9 tangent squared theta minus 4 equals 0. Give general solutions. Notice this one only has the one trig function, so we can solve it using square roots after we've isolated the tangent squared. Pause the video, give it a try. All right, here's your fair warning if you haven't paused the video yet. Solutions in 3, 2, and 1. On the first one, if we make the substitution of, let me get my pointer out here. Come on, cooperate. If we make the substitution secant theta equals u, the equation becomes 2u squared minus 5u plus 2 equals 0. That does factor. It factors into u minus 2 and 2u plus 1. If you didn't try factoring it, I would recommend foiling this u minus 2 and 2u plus 1. Excuse me, 2u minus 1. I'm sorry. So that should be a minus. But it does factor and gives you solutions of u equals 2 and u equals 1 half. And then change it back to secant of theta to get secant theta equals 2 and secant theta equals 1 half. Warning, 1 half is not in the range of secant. Secant is only 1 or higher or -1 or lower, not in between. So secant of theta equals 1 half has no solution. But secant of theta equals 2 has two solutions over the first period. Let me get my pointer back. In the first period, secant theta equals 2 has a solution in quadrant 1 and quadrant 4. The reference angle is pi over 3, and in quadrant 1, that's its solution. And in quadrant 4, it's 5 pi over 3. There's our general solutions. For the tangent problem, if we isolate tangent, we get tangent of theta equals plus or minus 2/3. Did you remember the plus minus? So solutions exist in quadrant 1 for the positive solution and quadrant 2 for the negative solution. Remember, for tangent, the period's only pi, so we look in quadrants 1 and 2. The reference angle for both is tangent inverse of 2/3, which is about 0.5880. In quadrant 1, that is the solution. In quadrant 2, we would subtract it from pi to get that solution, and then append the multiplier, the period multiplier, pi n, to both to get the general solutions.